Hello, my name is Kendle Lam, and this is Lab 1, Constant Velocity. So the purpose of this experiment was to compare an ideal computational model to the real-life model for an object traveling at constant velocity. And the models used were position versus time graphs from a tracker video analysis, as well as a glow script computational model. And for the main physics concepts, first of all, we got the momentum principle. And the main thing here is that as long as there's zero net force, there's going to be zero change in momentum, which means a constant velocity. And that's what we're trying to model in this lab. We also got the velocity update formula shown here. And again, showing that when there's zero net force, the final velocity will always equal the initial velocity at every point. We also got the position update equation right here, which shows how position changes over time using average velocity. And of course, in this case, the average velocity is always going to equal the initial velocity since we're assuming constant velocity. Another important concept is Newton's first law, stating that an object in motion will stay in motion unless an external force acts upon it. And these principles were used in this lab to model the object's motion in CloseScript. And finally, a preview of the main result of the lab is that the computational model, assuming zero net force, could not perfectly model the real life scenario. So for the setup of this experiment, we had the system being the golf ball, the surroundings being the earth, table, as well as air. Obviously, the friction from the table as well as air resistance were ignored in the computational model. And the position and velocity at t equals 0, the initial values are shown here, and those were just calculated from the first couple points in GlowScript, in Tracker. So here, looking at the tracking experiment, we can see the setup with the axes. This is the origin right here. So when I play the video, we can see that the golf ball starts at the origin and starts rolling to the left, which is the negative direction in this case. And we can see here that the position versus time is plotted here. It has a negative slope because it is traveling in the negative direction. And we can see it looks pretty linear, which is to be expected because we are trying to model something that is traveling at constant velocity. So now we're here in GlowScript to look at the code. Here we can have a look at the initial conditions right here, where I set the mass and the initial position and velocity of the ball, which I calculated before from Tracker. And here in the calculation loop, we can see that it runs as long as the time is less than 1.23 because that's how long the video took in Tracker. Right here we put set net force to 0 because we're assuming there's zero net force, constant velocity, and here are the velocity update equation as well as the position update equation that is used to update these two values. And right here, if we run the program, we can see that it looks pretty similar to the tracker video. And the position versus time graph also looks pretty similar. It's a downward slope as well. Here we can see that the velocity is just remaining constant since there's zero net force. So comparing the models, we can see that this orange line from the computational model in CloseScript, it is perfectly linear right here, and we can see that the blue line right here from Tracker, it starts off pretty close to the computational model, but as time goes on, it definitely veers off a little bit, and that is to be expected because the model did not include forces such as friction or air resistance, and that explains why in the real life model from Tracker, the magnitude of the velocity is decreasing over time because there is that external force acting upon it. So for sources of error, the low FPS and unclear background could affect the tracking software, and as well as if the camera angle and the ball path were not completely straight, that would also affect it. And the discrepancy between the computational and the real life model can be explained by friction and air resistance. So now let's discuss what would happen if we were to flip the axes. Well, the speed would remain the same because the velocity is simply changing direction. The magnitude of the velocity would be unchanged. The slope would change to positive. It would look a little something like this graph right here because the velocity would turn positive since the ball is now traveling in the positive direction instead of the negative direction. It would basically be like a reflection over the x-axis. And now let's discuss, is it possible to say how many pushes and pulls are added together to give zero net force? Well, in this case, you can have a general idea of contributing forces, like you'd say normal force and gravity cancel each other out in the y direction. But there are definitely less obvious interactions that are hard to account for. And the main point is that Newton's laws, they only tell us about net force, and just knowing that there's zero net force, that doesn't give you any information about which forces are summing to create that. Thank you for listening.